Hello, everyone. Welcome to the 12th talk of the Chromatic Nullstellensatz Seminar. Today we have Logan from UCLA. Logan will be talking about nilpotence detection. So Logan, please take it away.
All right, so today we're going to talk about the potence detection. We're going to start discussing the relevant situation that happens in chromatic homotopy theory, and then we're going to go into some generalities about tensor triangular geometry. All right, so as the first place to start, let's talk about the chromatic story. So in Lurie's notes, there's this proposition, which we're going to prove because it's a rather easy proof. So we're going to take a collection of ring spectra E alpha. Then the following are equivalent. 1. So we're going to work P locally. So if R is a P local ring spectrum, and we have a class X in pi star of R, then if for all alpha, X is equal to 0 in E star alpha of R, so this is under the map from pi star of R to E star alpha of R, then X is nilpotent in pi star of R. Condition 2 is the same, but star is replaced by 0. So this is something happening purely in degree 0. 3 is for X arbitrary P local spectrum. Then if we have some class X in pi 0 of X, such that it has trivial image in E alpha 0 of X for all alpha, then X to the tensor n as a class in pi 0 of X to the tensor n is 0 for some n greater than 0. And finally, for X arbitrary P local, and F a finite spectrum with a map to X, then if the composite to E alpha tensor with X is 0 for all alpha, then the nth tensor power of this map is 0 for some n much greater than 0. All right. So this isn't too hard to prove. So let's just do the proof. For 1 implies 2. This is clear, basically by definition, because if we see up here, we just plug in 0 for start, and then we win. All right. For 2 implies 3. We can take R to be the ring spectrum given by a direct sum of tensor powers of X. So this is the free E1 spectrum E1 ring spectrum associated to X. And then it is clear that the condition down here in 3 is satisfied. For 3 implies 4. A class X in pi 0 of X we can consider just as a map from the sphere spectrum to X. Or I guess rather let's do it this way. we're just doing it for arbitrary finite spectra, we can consider in this diagram here, we replace x in this statement by x to the f, because then we're going to have something like this. And then we use the fact that this class sits in pi 0 of this, and then we win. And for 4 implies 1, if we're given some class x in pi m of r, then this is corresponding to a map from the mth shift of the sphere spectrum to R. And this is going to sit here in condition 4. So this condition exactly is the same thing as saying that, so 1 and 4 are exactly saying the same thing in their hypotheses. If we replace f by this map x and applying 4, we see that for some n, this is equal to 0. And if we compose with the multiplication map on R, then this is exactly the class represented by x to the n in pi star of R. So that implies the condition 1. And if we have a map, that, a collection of ring spectra that is like this, we see that they detect nilpotence. So the big theorem here from the chromatic side of the story is, let me make sure I get the authors right, because I'm going to misspell one of their names, I'm sure. Devenant, Hopkins Smith. And they proved that mu detects nilpotence. And we're not going to prove this today because it's a very long proof. But this sort of is why mu is so interesting to study and why it really is at the heart of this whole chromatic story. In particular, you can use this to show that the pi greater equal 1 of the sphere spectrum, every element in here is nilpotent. Because if we recall, mu is a ring spectrum, so we have this natural map from S to mu. And really what this says is that the kernel consists, well, the full statement is the kernel of x, pi star x, to pi star of, so rather mu star x, consists of nilpotent elements. And using that, we see that under this map here, applying pi star to both sides, since pi star mu is the Lazard ring, it has no non-trivial torsion. And we know from, for instance, theorems by Serre, that pi greater equal 1 of S at each level is finite. So if you take pi n, the sphere spectrum for n is greater than or equal to 1, then this is finite. So it has trivial image under this map to mu, and therefore it must be nilpotent. So the main goal with the rest of this is going to be using this sort of nilpotence theorem in order to classify the Balmer spectrum of the category of finite spectra. That is the heart of this whole chromatic story, and that's where all these Morava-K theories come in, stratifying the different levels. So let's talk a little bit about some generalities about how stuff works here. I'm going to first recall some facts from tensor triangular geometry. All right, so our setup, we're going to have K is going to be some tensor triangulated category, or symmetric monoidal stable infinity category, if you will. And we're going to have that it's rigid, so every object has a dual. And I'm going to assume that it's also idempotent complete. You don't need this assumption, but it makes some of what I want to do later easier in terms of just the proofs. So it's going to be convenient for us today. All right. So in the setup, we recall that a TT ideal is a thick. So thick means closed under direct summons. If XO plus Y is in it, then both X and Y are. Triangulated subcategory. So we also want it to be full, of course. I, subset of K, such that if Y is in I and X is in K, then X tensor Y is in I. So basically the same definition you would want from commutative algebra of what an ideal should be. And this triangulated business just means this is closed under 2 out of 3 for arbitrary exact triangles. All right. And in particular, it is prime if X tensor Y is an element of I, implies that one of them is an I. So exactly the condition you would expect. Now we can define the Balmer spectrum. SVC of K is the set of prime ideals P together with a topology This is going to look a little bit different than the Zariski topology if you're thinking in terms of elements. If you think about it in terms of supportive modules, and this is pretty much exactly how you would define the Zariski topology. So we want closed supports. So it's generated by closed subsets, where we take the support of X to be those primes P, such that X is not in P, for X is an element of K. The motivation for defining it this way is not necessarily taking it straight from commutative algebra, but there's a whole notion of support datum where you want to say that you have these closed subsets of supports in some space. So compact support is sort of what you should be thinking of, such that these satisfy relevant properties with respect to taking direct sums, tensor products, and closing under exact triangles. So if you have all of these data, then this is going to be the terminal topological space with these data. And you can prove this, that's a theorem, that this is really universal in that sense. So that's why this is a good definition. All right. So in particular, this, I guess I should note that here, this rigid assumption is controlling the size of K, so it says K is usually small. Generally, the setup we're going to have is we're going to have some big triangulated or stable infinity category T, and this is going to have K sitting in here as the compact objects. And there's a bunch of variations on this where you don't want to assume some rigid hypothesis or you only work with the rigids. It depends on what you're doing. And there's also theory of sort of spectrum for the big category developed by Balmer-Favi and the theory of Balmer-Favi idempotence, which has been useful, for instance, in Clausen and Schultz's recent work on complex analytic geometry. Okay. So those are some basic notions. Now let's get to the main point of today, discussing nilpotence in this setup. Okay. So we're going to say that a map, so let's say a functor F maps K to L between TT categories. So I want this to be symmetric monoidal. I want it to preserve the duals. And I want it to be exact. So we're going to say it detects nilpotence. If F of a map F equal to 0 implies that F to the tensor N is equal to 0 for N much greater than 0. Okay. So the main theorem we're going to try and prove is that if F from K to L detects nilpotence, then the map the other way on their spectra is surjective. This is going to be comparable to this whole chromatic Nullstellensatz business we saw from this paper last year, where I believe they proved that using their constructible spectra, which as a side note, I've talked to Tomer and he thinks that it might just be equivalent to the Balmer spectrum appropriately defined. That if you have a map between rings there, the TN local rings, then it detects nilpotence if and only if it induces a surjection on their constructible spectra. All right. So this is sort of, I guess, a precursor to that in a sense. So let's try and prove this. All right. So what we're going to do is we're going to pick a prime P in the spectrum of K. And we're going to define the ideal J to be the thick triangulated subcategory generated by the image under F. And we're going to let S be the image of K without P. So this is some multiplicative set. And our goal is going to be to prove that J intersection S is the empty set. So if we have this, then we can win. Let's show how. So the idea follows this very common idea in tensor triangular geometry, which you might remember from classical algebraic geometry. Let's say, why will this work? Well, given an ideal I and a multiplicative set S, so this just means that if X and Y are in S and X tensor Y is in S, and we also want the unit object 1 to be in S, then if I intersection S is the empty set, we can extend I to a prime ideal P with P intersection S the empty set. All right, so let's prove this fact here. So what we're going to do is a usual sort of Zorn's lemma type argument. So let Z be the set of J TT ideals such that I is contained in J and X tensor S is an element of J for some S and S implies that X is in J. All right, so first, let's note that Z is not empty. That's always a good thing to have. And this is just because we can take J to be the ideal of all of those X and K, such that X tensor S is in I for some S. Now this is disjoint from S because you can see that if we had any T as an element of S intersection J, then there exists some S and S such that T tensor S is an I, but this is also an S. So that would be a contradiction. So therefore, this is disjoint from S still, and to see that it's an ideal, to see that it's thick is rather clear using the fact that tensor product commutes with direct sums and I is thick. The second point we're going to have to show is that it's closed under tensor products, but this is clear because if we have that X tensor S is in I, then Z tensor X tensor S is an I just from the fact it forms an ideal. And finally, for exact triangles, if we have X to Y to Z, let me not use the same letters, I guess. Let me use A to B to C, to sigma A, with A and B an element of J, then that means that there's going to have some S such that A tensor S is an I, and a T such that B tensor T is an I. And then we can just take A tensor S tensor T to B tensor S tensor T to C tensor S tensor T. Note that these first two are an I, and then so is the third by 2 out of 3. And this S tensor T is an S. So therefore, this actually is a tensor ideal. Okay, so now that we have it's not empty. And if we had any chain J1 subset J2 subset dot dot dot, we can just take the union over I of Ji. And this is easily checked to satisfy the same properties. So this is going to be in here. So therefore, Zorn's lemma applies, and we can get by Zorn some maximal P in this set above. And we claim that P is prime. So suppose X tensor Y is an element of P, and X is not in P. Now we're going to see where the assumption I used earlier on idempotent completeness comes in handy. So if K is idempotent complete, and in particular, you don't actually need this assumption. I think you can just get rid of it just by adding radical in what I said earlier, but I don't want to do that because it's annoying. So X tensor X dual. We have this splitting from the fact that K is rigid. So this is the identity. So that means that X is a direct summoned of X tensor X dual. So in particular, using this in induction, you can see that every TT ideal I is thick, is radical. So that means that if some power of X is in here, then X is in here. So since X is not in P, and P is some TT ideal, this implies that no tensor power of X is. So in particular, if we take S prime to be the set of X to the tensor N tensor S, such that N is greater than or equal to 0, and S is an S, this is multiplicative. And none of these are going to be in P. And in particular, by this assumption here, we see that S prime intersection P is the empty set. So that means that we can take another ideal Q, similarly to how we defined J up here, to be the set of those Z in K such that Z tensor S is an element of P sum S in S prime. And then note that Q contains P. Q intersection S prime is the empty set for the same reasoning as earlier. And in particular, Q intersection S is the empty set. So by maximality of P, that means P equals Q. But we have in particular that Y is an element of Q since Y tensor X is in here, is in P. So Y is an element of P and P is prime. All right. So by this, if we can prove that this J here that we defined earlier, this image of P, the ideal generated by it, and this S, the image of K without P, we can prove that these are disjoints. And we can extend to some prime ideal Q in L such that the inverse image of Q is going to be P because it contains P, because it contains the sense Q contains the image of P, and Q is disjoint from the image of K without P. So if this is the case, then we will be done. All right, so we've now reduced to showing that this J intersection S is the empty set. In order to prove this, we're going to use one more lemma. So this is going to be an explicit way of describing the TT ideal generated by some element X. So let X is an element of K. You can actually do this under much weaker assumptions where you only need to assume that X is dualizable. You don't have to assume that K is fully rigid for this lemma to hold. And take the exact triangle. So we're going to have Y mapping over by Z to the unit, which is going to map in by the unit for the adjunction of X and X dual. And then mapping off to the cone, to the shift of Y. I'm going to call this triangle. All right. Then the ideal generated by X is nothing but the set of Z, it's an element of K, such that C to the tensor N, tensor Z, is equal to 0 for some N much greater than 0. All right, now let's prove this. Okay, for containment, note that X tensor Z is equal to 0, since X tends to X tensor X dual splits, and tensoring with X is exact. And then in particular, this means that X is an element of the right-hand side. So, oops, wrong way. Rather, I should say, yeah, messing myself up. This is the next part. Instead here, what we can do is we can take the quotients by this ideal generated by X, and we're gonna look at Z mapping in here. So if we look at this exact triangle in this quotient, then X goes to 0, and 1 is gonna go to the unit. So that means that this is going to go to an isomorphism. And in particular, if Z tensor this isomorphism to the tensor N is 0, then this implies Z equals 0 on the quotient. which implies that Z is an element of this ideal. So that's one containment. For the other containment, we use the fact that X to X tensor X dual splits. So this implies that X tensor Z is equal to 0. And so it suffices to show the right-hand side is an ideal. To start with this, we're going to note that it's closed under direct summons. So it's thick. Closed inner tensor products. Because if we have anything else, we can just append a tensor product here to Z, and this equation is still going to hold true. And finally, we have to check exact triangles. So for this, if you have A to B to C, to sigma A, with A and B is an element of the RHS, right-hand side, then we can take N and M such that this tensored with A is 0, and this tensored with B is 0. And then you can form a commutative diagram. So you can assume, without loss of generality, by increasing N or M as necessary, that N is equal to M. And then we can just do this. Y tensor 2N tensor A, mapping to Y tensor 2N tensor B, to Y tensor 2N tensor C, to Y tensor 2N tensor sigma A, Y tensor N tensor A, Y tensor N tensor B, Y tensor N tensor C, and this map here is going to be, let's say this composite here is going to be sigma tensor 2N tensor C. And these two are both going to be, let me not use yellow, that's a bad color. Very hard to see. These are both going to be 0. And this is going to be 0 by assumption. So because this composite here is 0, this implies that there exists a map this way, which we can call H, such that this triangle commutes. And since, let's see, this composite here is 0, this implies that there's going to exist a map this way, K, such that this triangle commutes. And then we see that this composite is going to be the same thing as doing, first going by H down to this way. And then you compose across. Now this composite here is 0, and then you compose by K. So in particular, it's 0. So therefore, B is in the right-hand side, or C rather. And therefore, we have the claim. All right, so let's go back to our setup from before. We can write down the definitions again so that we don't forget. J is the ideal generated by f of P. S is the image of K without P. And we want to show that these are disjoint. So suppose, towards a contradiction, that there is Z in K without P, such that f of z is an element of J. So in particular, note that J is equal to the union over X in P of the ideal generated by f of X. And so there's going to exist some X in P so that Y is an element of the ideal generated by f of X. Or rather f of z, I should say, not Y. Now, in order to see from here, we note that f of z is an element of this ideal, is going to imply this by this equivalence from before, that z is in this side, or rather f of z. So let's note that we have the exact triangle x from yx to 1 to x tensor x dual to sigma yx. If we apply f to this, then we're going to get f of yx going by this to 1 because it's symmetric monoidal, to f of x tensor f of x dual, again because it's symmetric monoidal, to sigma f of yx. And in particular, this is exactly the same sequence that we would see for delta f of x, so that f of this is equal to the same thing for f of x. And going by our condition from before, this ideal generated by f of x is the set of A in L such that z f of x tensor n tensor A is equal to 0 for n much greater than 0. So this implies f of z tensor f of z to the tensor n is equal to 0 for n much greater than 0, which implies, well, this here is just equal to f of z tensor z x to the tensor n is equal to 0. But note that this here is in K. So by nilpotence detection, we have that z to the tensor n x to the tensor m is equal to 0 for m much greater than 0. But z is a summand of z to the tensor m, well, z to the tensor 2 at least, and then each repeat inductively. So, well, tensored with z dual. This here implies that z to the tensor m tensor z to the tensor n x tensor m. So you can just pull this in here. It's equal to 0. So this is some power of z, and this here is a power of z. So this implies that z to the tensor m is in the ideal generated by x, which implies that z is as well. But then z is an element of P, and z is an element of K without P. A contradiction. All right. So this sort of nilpotence detection theorem is really what is used all the time in tensor triangular geometry when you want to classify the tensor ideals of some tensor triangular category. You come up with some nilpotence theorem, and then you use this to deduce that you have all of the prime ideals coming from something which is a priori much, or well, hopefully at least much easier. So as one rather silly example, we use something a little bit more accessible, some rings. So this first example, we're just going to work with the derived category of Z, the compact objects. So these are perfect complexes in Z. Then the TT ideals contain, as our primes, we have this for every prime P, we can take the kernel of dperf of Z, mapping to dperf of Z localized at P. And this is going to give us a prime ideal corresponding to P. And we can also have the kernel of mapping to Q. These are exactly the primes showing up from the spectrum of Z. And these are all of them. One way you can show this is by showing that this, something like this, detects nilpotence. And you reduce to a local case and check it locally. All right. This is a sort of general phenomenon that if we have, let's say, K a TT category with unit object 1, then there's a map from the spectrum of K to the good old ordinary spectrum of pi0 of 1. So these are the, by pi0 of 1, I mean pi0 of the endomorphisms of 1. And the way we see this is we're going to take, for every endomorphism, for every prime ideal in the endomorphism of 1, rather, let me do it the other way. So if we have P in the spectrum of K, then I'm going to map P to the set of F in pi0 of 1, such that cone of F I'm not sure if it should be in or not in. We're going to find out by the proof. I'm going to change this if it should be the other way. We'll find out. Wait. It should be not in. Yes, it should be not in. Okay. Yeah. Because you can think, for instance, if we're going here in the case of Z, then the kernel of this is going to consist of everything which is torsion of order prime to P. And so it's going to have the cone of every element which is not, which is prime to P. So we're going to want everything which has cone not in here. Yeah, and 0 is cone the unit, so we want 0 in there, and we obviously don't want 1 to be in there, so we don't want the cones to be in P, because 0 is in P, and that's the cone of the identity. All right. So we have to show that this right-hand side here is a prime ideal. To see this, we're going to suppose that we have F and G is an element. Let me call this ideal IP. Well, I guess it's a priori not an ideal, but let's show it's an ideal. So we have f comma g is an element of IP. Actually, I think this one is probably a bit harder, so let me do this last. We take f and IP and g arbitrary is an element of pi 0 of 1. Then we can take 1 mapping to itself by f. Then we can map over here by g. We can go ahead and take cones. So here's going to be the cone of f. It's going to be the cone of g. This is going to be the composite gf, which is g times f. This is going to be the cone of gf. This is just our octahedral axiom here. Let's go the other way. Actually, is this what I want to do it, or do I want to tensor? There's a couple ways you can set this up. I'm just trying to think about which way is probably the best. We'll just see how it goes. Okay, so we want to show that this is not in P. Another way to set this up is we can take some. I found a tensor there or not. Okay, let's actually expand this to a bigger diagram where we're going to tensor these two sequences together. Here's cone of f, sigma 1. I want to tensor with g here. This is going to be the map g. This is also g. Here's 1, here's f. Cone of f. Here I'm acting by g. Going off to sigma 1. Here I'm going off to cone of g. And then off to sigma 1. Similarly here. And then here we're all acting by f. This here is the cone of g tensor the cone of f. And we're going to have exact rows and columns in this diagram. So what we can note is that if cone, let's see, the cone of fg is the cone here of this here. So let's suppose that this is in P. Then in particular, sorry, it's been a while since I've done this. I'm trying to think of the right way to go through this one. If cone G is in P, then this is obvious because by 2 out of 3, then this won't work. So the only issue is when cone G is not in P. All right, let me write down the part. So if cone G is in P, then this cannot be in P, or else this exact triangle here would show that this is in P, and that would be a contradiction. So you're only left with showing that this isn't the case if cone G is not in P. And for this, let's see. Let's look at the map from K to K mod P. Then cone of F goes to something non-zero. Cone of G goes to something non-zero. And then we're going to have the unit in here in K mod P. You can map over by F the unit here in K mod P. Here's cone of F. Similarly, we can do the same thing with cone of G. And let's see. So we're supposing that this is non-zero here in this localization. We're supposing the cone of G is non-zero in the localization. And we claim that the cone of GF is not equal to 0. So this last condition is equivalent to 1 in this localization. Mapping over to 1 here. So here's F, here's G. And we claim that this composite, all right, so this being non-zero means that this is equivalent to F is not a unit in 1 K mod P. This is equivalent to G is not a unit in K mod P. And if these are not units, then their composite is not a unit either, because it's a ring. So this implies the claim. And now we have to check that if F and G are in the ideal associated to P, then this implies that F plus G is. This one I believe is mildly annoying. Don't remember if I remember how to do it without trying to work it out. So we'll find out. All right, so we have a diagram like this. And here we have this. This is mapping the diagonal. And if we wanted to take F plus G, then that's this composite here. This is the projection along the diagonal. So this is 1, 1, and this is 1, 1. All right. So again, we can use the idea to work locally. So our claim amounts to that if we recall that the elements of IP are precisely the non-units in K mod P, then this reduces to the sum of non-units in pi 0 of 1 K mod P is not a unit, which is equivalent to pi 0, 1 K mod P is local. And for this, we're going to note that okay, all right, so we want to show this claim. And can you do this from this diagram up here? I mean, this should reduce like something that's showing that this is some local TT category, but you watch me try and figure out how to do it live. Let me set up this full diagram here. We can look at all the exact triangles associated here. All right, so we want to claim that this is not an isomorphism. Given that F and G are not isomorphisms. In particular, we're working in K mod P. So we're working locally because otherwise it would not be true. And for this, let's see. You can set it up like this. All right, let's just start taking exact triangles. Call this Y. And we also have on the other side something like this. Actually, let's not do this way, let's do it the other way. We're just gonna go here. We're gonna go in by FG. Then we're gonna map back to 1. The cone here is just going to be a shift of 1. The cone here we define to be Y. With this map this way. This is the cone of F plus G here, which is what we want to show is non-zero. We have this here, we have this here. All right. And let's see. So we have this 1 mapping to Y, mapping to the cone of F plus the cone of G. Back on this side, up here. And then we also have this exact triangle here, which we can shift back by 1 to get a map from 1 to y. To the cone of f plus g. And if we note that this map from 1 to y here factors as going up this way and then projecting off down, then this is equivalent to this map projecting off to y down here. And before we have to include by 1 comma minus 1. So this is going to be 1 going in by 1 minus 1, 1 o plus 1. And then we're going to map off to 1 by this map here is 1 minus 1. And then we're mapping over to y. Then we compute this total map is just the same thing as 2 times the map going up from 1 to y. So if we're going to first compose the 2 and then we're going to do this, this is 2 times this map. Wait, is this what I want? Okay, I mean, either way, this map still factors this way from this going into here, from the fiber of this map here. And then you compose the cofiber of this map. And then you go into y. So what we're going to get is yeah, it should be what I want, but whatever. I can do this here. Which way am I going here? Oh yeah, I want to go the other way on the bottom. Right, yeah, so this is the multiplication by 2 map. And then we go into y. This y up here, this map here, this map here. This full map is this one. Oops. Undo. So we can take up here and map up here by multiplication by 2, map by the identity on y. Here we have the signal 1s. And this is going to induce a map here. And we just want to show that this guy here is non-zero. And in particular, we should be having to use some sort of a tensor here. Okay. I'm clearly messing something up, but I'm too far over, so. Palmer has proved this somewhere. I'm looking through my old notes now to see if I'm going to see what I'm missing, because this is the tricky part of it. You can feel free to end it if you want.
Maybe you can just add it in the notes.
Yeah.
Yeah, we can probably do that. You can maybe add it just in the notes.
There's some trick to it. It amounts to showing, well, I mean, you know that K mod P is local. So it amounts to showing that if you have something which is local, which means 0 is the minimal prime, then you have this, then the associated ring is local. And that's what I'm messing up here. Here it is. Okay, I found the proof here. Here's the actual sketch. I can just do this real quick. You have to show that if A is in the endomorphisms here, this is for any local TT category, which just means that 0 is the unique minimal prime. Then A squared times the identity on its cone is 0. You can show this by a similar trick to what we used earlier. And let's see. After you have this, then you take any A and B in the endomorphisms of 1. So by here, I mean pi 0 of the endomorphisms of 1. So these are not invertible. Then cone of A is not equal to 0. Cone of B is not equal to 0. By the local property, this implies that their tensor product is non-zero. And then A plus B times, that's the trick. A plus B is nilpotent on this. Yeah. Okay, that's the trick. To show that this fact here, this is actually not too hard. For this one, you're just taking like 1 times A, 1. It's a very similar trick to what we used earlier. And then down here, dot A, dot A. Let me expand this diagram a little bit so that it's a bit easier to see. We can just name all of these. And in particular, what we can do is we can note that we have a map down this way, just given by the identity, which admits that this is homotopic to this. This would be kind of A. And then you just do this, append the same diagram. and use the same trick from earlier where you factor this way and this way. So that the red composite is equal to the blue composite, and then the blue composite is 0. All right. Okay, now we're done.
Cool. Thanks, Logan. So let me probably stop the recording.